Here's the solution to quiz number 2 for ECE 320 Electronics for fall 2022. The first question, part A, asks what are electrons and holes? Well, for electrons, you can just go to Wikipedia. Okay, this is an online quiz. Chegg, I highly discourage. Do not use Chegg, but other online resources, textbooks are fine. An electron is just a negatively charged particle that forms a covalent bond and moves around to carry current. A hole is a missing electron in a covalent bond. Holes can also move and carry current. However, a missing negative charge is like a double negative. It acts as a positive charge. So semiconductors have both positive charge carriers, holes, and negative charge carriers, electrons. Part B, the voltage drop across a silicon diode is 0.7 volts. If you heat it up, what happens and why? Well, when you heat it up, the temperature or the voltage drop across the diode decreases. One way to explain that is the voltage across the diode is related to the doping relative to the intrinsic carrier concentration. This is the number of thermal holes and electrons. If the number of donor atoms relative to the number of thermal electrons and holes is large, I have a larger voltage, like 0.7 volts per silicon. As the thermal electrons goes up, the doping becomes less significant and the voltage drops. One way to explain it. Problem 2. If I take an 0603 resistor and I want to make it a 1714 ohm resistor, what doping do I need? So this is an 0603, two sides. The resistance is resistivity times length over area. Plugging in numbers, the resistivity is 17.14 ohm centimeters. Whenever that's the conductivity, which is the number of charge carriers times the charge per carrier times the mobility. Mobility of electrons, or actually mobility of holes, since this is p-type semiconductor, is 500. So that'd be ends of p. So the doping of the boron would be 7.29 times 10 to the 14th atoms per cubic centimeter. Problem 3 is if I used a thermistor, suppose the thermistor had this characteristic, I put it in a circuit and I measure 7.3 volts. What's the resistance? What's the temperature? Well, from voltage division, I know that the voltage is RT over R plus RT times 12. Solving backwards, RT is 7.3 over 12 minus 7.3 times R, or 2662 ohms. Plugging in 2662 right here, and solving backwards gives you a temperature of 19.27 Celsius. Problem 4. Draw the load line and find the operating point. Well, the load line, the x-intercept is when this is an open circuit, when ID equals 0, the x-axis, I'm going to see 10 volts. On the y-axis, when the voltage is 0, I have 10 over R, which for 1714 ohms is 5.83 milliamps. 2 points determines a line. Where the line intersects your curve is your solution. That's load line analysis. Problem 5. Write the equations for this circuit. Now what I would do, let's make this smaller so you can see it. Start with the diodes. The voltage across the diode goes anode to cathode. Anode to cathode, anode to cathode. For diode 1 is V1 minus V0, that's anode to cathode. Diode 2, 0 minus V3, anode to cathode. Diode 3, V1 minus V2, anode to cathode. Then the voltage node equations at node 1, these currents add to 0, and that's V1 minus V0 over 100, plus ID1, plus ID3, plus V1 minus V3 over R. At node 2, it's minus ID3 plus V2 minus V4 over 400. Diode 3, V3 minus V1 over R, plus V3 minus V4 over 300, minus ID2. At node 4, V4 minus V2 over 400, plus V4 over 500, plus V4 minus V3 over 300 equals 0. Gives you n equations and unknowns. And another one, same procedure. To start, write the voltage drop across the diode anode to cathode. For diode 1, it's V1 minus V2. Diode 2, 0 minus V2. Diode 3, anode to cathode, V1 minus V3. Diode 4, V3 minus 0. Then your node equation. At node 1, the current left is V1 minus V0 over 100 plus ID1 plus V1 over R plus ID3 equals 0. At node 2, minus ID1 minus ID2 equals 0. Node 3, minus ID3 plus ID4 equals 0. So that is quiz number 2 for ECE 320 for fall 2022.